Okay, let's start the lecture. First, we revisit about what we studied last time. So last time we talking about the weak interaction. Weak interaction is a messenger particle. It's a W plus minus boson and G boson, and they are very massive particle. So they will be unstable particle. We will study last times, and also, the nature of the weak interaction is very similar to electromagnetic field, so they having also vector and scalar potential. But it's only different things. The weak interaction is connected by massive boson, and also such kind of massive bosons are found in 1983. So, to describe the G boson, in this case, we can modify Maxwell equation with a mass term. So here mass term is here. So, and this is very large. So we cannot ignore such kind of the mass term. And to satisfy such kind of the Maxwell equation, the G boson potential defined by G boson particle in terms of the classical static potential given by very similar to magnetic field case. And then from of this equation, you can find out that the dispersion relation in terms of the spatial relativity, that 2 E square equal to P square and M square. So in this case, there are still mass term in dispersion relation. So we can now know that the such kind of weak interaction, they interacted by massive boson. And if we found the static solution for such kind of the potential, then we can find the very similar to Coulomb potential, but with exponentially decreasing term. So weak interaction interacted by massive boson, so the force of the potential decrease very faster than electromagnetic case compared with Coulomb potential. Then also we found the quasi-static solution. The range of the weak interaction covered the space very short. So around the nuclei, we just consider such kind of potential or density of the G boson very static value. So we just treat this such kind of the density as a constant. Then we do about the integral by parts. Then we found the static potential about the G boson. And for the distribution, again, talking about this, and we finish drawing the drawing the checking of the mean life and half life. So most of the unstable particle only exists at the transition process in terms of the Feynman diagram, like this. So very short time they are lived. So I define that the mean life is the mean time particle exists in isolation. And to calculating about the mean life, we define the function of the time t. It is defined to the probability that the particle survive for time t. So if we insert the time t, then we can find out that the probability the particle can live. So I introduce about the function of the function of the time of t plus dt and their relation to time t. So t plus dt is a final state and t is the initial state. So at the the particle to exist at the t plus dt, and the particle should be alive at the time t. So, and we assume that the constant probability 1 over tau unit time. Then we construct such kind of relation. So let's go further today. From the above equation, t plus dt in this case very infinitesimally small value, so we can expand this equation by power expansion for dt. So initial the leading term dt equals 0. So and the second term p t dt and dt, and there are other higher order terms still living that, and also this equation should be same to above our from the this equation, so it should be satisfying. Minus pt and dt tau, and higher order terms is very small, we can ignore them. So these two equations, this one and this one, they should be coincident to each other term by term. So the first term pt is just same to each other, and the second term should be coincident to that. Then you found that from this equation. T equal to minus e tau. Then to do an integral, let's move the p left hand side and t move to right hand side. And we found that p p here t. So p this t remove each other. Then equal to minus 1 over tau. Then by doing an operate integral to both sides, so integral to this equation, and we found that so the function of t in terms of the time t with integral constant c0, then they return exponential minus t tau. So insert O 0 and P 0 equal to C0. So C0 means the probability for a particle living at the time equal to 0. So it is initial condition for particle existence. But normally we think that the starting time the particle should be live. So it can be just 1. Then we found that the probability function equal exponential minus what up. So now we found that the probability of a particle living at the time t. So using of this, we can find the mean time or mean life. So that the mean life the expectation value of time t. So expectation value of the kind of time t the particle's life. So let's do this. So expectation value time t equal to 0 to infinity time t, and in this case the t means the expectation value of the life of the particle. So we need to their expectation value of their life for given time t. So this is time for life. Then during this time, the particle number of so during this time, during time dt, and the particle decaying with the ratio of 1 over tau. As we construct such kind of equation, post equation for the last time. So this is a kind of decay probability. Once more, this is such kind of existence multiplied by ratio of decay. Then we need to integral by part. Rho to infinity time t exponential minus t over tau and dt tau. Then let's do the integral by part. One over tau minus tau to infinity to infinity d. This one's still t. Minus tau t. Then the first term can be minus and t equal 0. Then it should be 0. So 0 to for infinity and 0 for t. So the first term should be 0. Then the second term being so this is becomes tau. So the expectation value for the mean life will be tau. But normally, we can not easy to always we not easy to waiting for the time tau t pass away pass. So we define such kind of the particle life in terms of the half-life. And this is denoted by T1/2. This means that 1/2% or 50% probability that the particle has decayed. So this is means that half-life. Then the value of the half-life quite easy. The probability at the half-life O, then only 1/2 particles are living in our system. So potential minus large T 1/2 over tau, then log both sides. So the half-life for any particle tau log 2 by number it is 0.6963 tau of time or second passed after it starting. And normally we 1/tau is called decay rate. So in next lecture we just some visit about some nature of leptons and their reaction. So let's revisit what I know about the lepton. Lepton is a fermion spin 1/2 particle. They interacting by electromagnetic field and weak interaction, but there are no strong interaction. And there are 6 leptons in our nature: electron, muon, tau, and electron neutrino, muon neutrino, and tau neutrino. And also they having a magnetic moment. approximately EH bar 2. And the magnetic moment is anti-aligned with spin. And such kind of electrons can be annihilated by when they meet antiparticle. E minus plus E plus equal to 2 gamma, 2 photons they produced in this case, and or sometimes more many photons can be produced in their mid. So in this case, the number of gamma always large, more than 2 according to energy and linear momentum conservation. And antiparticle muon, Newton muon, and tau all of the H is similar to electron, their mass, and the muon, due to their mass, they use to prove of nuclear charge density. And also, neutrinos also having their anti-neutrino. So let's see about the detailed things about the muon and weak interaction. So I already said that massive particles are unstable. Instability of the heavy leptons. So now we already many classical relation between the Maxwell equation and G boson. Now let's see about the W plus minus bosons in this case. Because they having a charge, so they some having a relation between the electron and weak interaction. So we consider in this case W plus minus boson. And they're having some rule. in beta decay. So most interesting reaction related to beta decay about the neuron. So first let's see about the reaction equation for neuron decay. Mu minus equal to muon neutrino and electron and anti-electron neutrino. In this case, we already studied about that. The muon So such kind of the reaction between the left hand side and right hand side, W plus minus boson meditating are like virtual process. And muon having a negative charge, so we need to, in after reaction, we need to negative charge, so electron can be produced in this case. And also, so due to that, the muon decay, the W plus minus boson produce electron related to charge conservation and energy conservation. So let's see muon decay. There are two processes about the muon decay. One, your minus just starting to the Feynman diagram. So somewhere muon neutrino produced and electron produced. And electron and anti-electron neutrino produced. But their arrow is opposite because they are antiparticle, and W minus boson working here. So boson denoted by wiggled line and antiparticle opposite direction of the arrow. So this is about the post muon decay. Antiparticle. And also the second reaction very similar. But this is interacting by W plus boson. So in this case, the minus charge in post process going to this. But in this case, the direction of the W boson going to upside, and the plus charge go up, then the negative sign goes to same to down. So charge is still conserved in this case, but W plus minus boson moving rate different opposite to each other. So this is 2 muon decay in our nature. And after that, such kind of the wiggled line very living short time. So W plus minus boson finish their working, then they disappear because they are very unstable particle. So here we consider conservation of plus minus charge. And also it is the same to conservation of lepton number. So for example, muon just one lepton. So in terms of the muon number plus 1, and neutrino, muon neutrino plus 1, and electron plus 1. but anti-electron neutrino, anti-lepton, so -1. So in left-hand side and right-hand side, the lepton number should be conserved in this case. Okay, finish today at here, and we will study about the parity violation in muon decay and their aligned of momentum. Okay, stop here.